For centuries, the nature of consciousness has baffled philosophers, scientists, and thinkers alike. At its core, consciousness is the awareness of our own existence, the experience of being alive and thinking, feeling, and perceiving, the firing of neurons, the synapses, the intricate networks of communication. All of these contribute to our conscious awareness. Yet this perspective begs an essential question. How do the firing of neurons create the rich tapestry of subjective experience we call qualia, that ineffable feeling of seeing a red apple, tasting chocolate, or feeling the warmth of the sun on our skin? These experiences seem to transcend mere physical interaction. How can something so intangible arise from a physical system? This dichotomy between the objective processes of the brain and the subjective nature of experience forms the crux of the mystery. The brain, with its billions of neurons, generates complex patterns of activity that correlate with our thought, emotion, and sensory perception. But these patterns don't feel like anything in themselves. So, where does the feeling of being come from? This is often referred to as the hard problem of consciousness, a term coined by philosopher David Chalmers. While we may understand how the brain processes information, we still don't understand how or why it results in the subjective experience of awareness. On one hand, consciousness appears to be a product of evolution, a mechanism to help organisms navigate and survive. The ability to reflect on one's surroundings, make decisions, and predict future outcomes would be invaluable for survival. Yet we also experience consciousness as something deeply personal, even spiritual. People throughout history have pondered whether consciousness is a fundamental aspect of the universe, something that exists independently of the physical world. Some have argued that consciousness could be a property of the universe itself, like gravity or electromagnetism, something that transcends the physical body and pervades all existence. This notion resonates with ancient philosophies, where consciousness was often considered a universal force present in everything from stars to trees, and even inanimate objects. However, the scientific perspective leans toward a more reductionist view, where consciousness is seen as a phenomenon emerging from complex systems of brain activity. This viewpoint suggests that the mind is the brain, that our conscious awareness is an epiphenomenon, a byproduct of neural process. But is this sufficient to explain the richness of conscious experience? Is it enough to simply say that the firing of neurons causes us to feel? The contrast between the physical and the experiential has led to intriguing theories. Some propose that consciousness could be akin to a quantum phenomenon, a result of quantum processes within the brain. This speculative idea, known as the orchestrated objective reduction, Orch-OR theory, suggests that quantum mechanics plays a role in the emergence of consciousness, hinting at a deep connection between the mind and the fundamental fabric of reality itself. The quantum world, with its strange and mysterious behaviors, such as particles being in multiple states at once, or the entanglement of particles across vast distances, offers a tantalizing possibility that consciousness might not be confined to the brain, but might instead be a universal phenomenon that connects all of reality. On the other side, there's the theory of panpsychism, which posits that consciousness is a fundamental quality of matter itself. According to this view, everything in the universe, atoms, molecules, planets, has some degree of consciousness. While this might sound far-fetched to many, it offers a provocative answer to the problem of how consciousness emerges. If consciousness is a basic property of all matter, then it doesn't need to emerge from somewhere. It's already there, embedded in the very fabric of existence. Regardless of which theory resonates most, one undeniable fact persists. Consciousness is deeply personal. It's our gateway to experiencing the world, to making sense of the universe and our place within it. It allows us to question reality, to dream, to create, and to love. It connects us to each other and to the cosmos. Understanding consciousness may not just unlock the mysteries of the brain, it could reveal the very nature of reality itself. But for now, the mystery remains. As we continue to explore the vast frontiers of science and philosophy, the question remains as compelling as ever. What is consciousness and where does it come from? The answer, as elusive as it may be, might hold the key to understanding not just our own mind, but the universe itself. What if the smallest particles hold the secrets to our thought? Quantum mechanics is often regarded as one of the most revolutionary and perplexing scientific theories ever devised. Unlike classical physics, which deals with predictable and deterministic laws, quantum mechanics unveils a reality where uncertainty reigns and the boundaries of what we can know are constantly challenged. To understand this strange realm, we need to explore three of its foundational principles: wave-particle duality, superposition, and entanglement. At the heart of quantum mechanics lies the concept of wave-particle duality. Traditionally, we think of light as a wave and particles like electrons, discrete objects. However, in the quantum world, particles such as electrons and photons exhibit both wave-like and particle-like properties, depending on how they're observed. This phenomenon was first observed in the early 20th century during the double-slit experiment, where particles fired at a screen through two slits would behave as if they were waves, creating an interference pattern rather than behaving like solid particles. This duality shakes the very foundation of classical physics, where objects were always classified as either particles or waves, never both. What does this mean for our understanding of reality? Imagine that light, which was once thought to be just a wave of electromagnetic radiation, can also behave as particles called photons. Similarly, particles like electrons, which were once thought to be small, solid objects, can also behave as waves. This dual nature confounds the intuitive understanding of the world, introducing a level of uncertainty at the most fundamental scale of matter. The next concept that defines quantum mechanics is superposition. In classical physics, objects have a definite state. A coin, for example, is either heads or tail, but never both at the same time. In contrast, quantum particles can exist in multiple states simultaneously. A famous example of this is Schrödinger's cat thought experiment. A cat in a box is both alive and dead until observed. In the quantum world, particles such as electrons can exist in multiple places at once, being in a superposition of different states until they are measured. This idea extends to the very fabric of reality itself, suggesting that before observation, the universe exists in a haze of potentiality where every outcome is simultaneously true. It's only once an observation is made that one outcome collapses into reality. This strange property leads to a fascinating paradox. Quantum particles do not have a definite position or velocity until they are measured. Instead, they exist as a probability where a cloud of potential outcome. For example, an electron surrounding an atom doesn't travel along a fixed orbit, but rather exists in a probabilistic cloud described by a wave function. Until we observe the electron, we can't pinpoint its exact position. This uncertainty is not due to limitations in our technology, but is a fundamental aspect of the quantum world, a concept codified by Heisenberg's uncertainty principle. According to this principle, there are inherent limits to how precise we can know certain pairs of properties, such as an electron's position and momentum, simultaneously. The more accurately we measure one property, the less accurately we can measure the other. The final principle we'll explore is quantum entanglement, a phenomenon that Albert Einstein famously referred to as spooky action at a distance. When two particles become entangled, their states are linked in such a way that the state of one particle immediately influences the state of the other, no matter how far apart they are. This means that if you change the state of one particle, the other particle's state will change instantaneously, even if they are light years apart. Entanglement challenges the classical idea that information can only travel at the speed of light, and it seems to suggest that particles are connected in a deeper, non-local. Entanglement has profound implications for our understanding of the universe. It suggests that at the most fundamental level, everything in the quantum world is interconnected, as if particles share a hidden, instantaneous connection that transcends time and space. This mysterious property has been experimentally verified in numerous experiments and is now the basis for emerging technologies like quantum computing and quantum cryptography. When we contrast quantum mechanics with classical physics, the differences are stark. Classical physics, governed by the laws of Newton and Einstein, operates in a world where objects follow predictable paths and behaviors. A ball thrown into the air follows a clear trajectory, and the outcome can be predicted with certainty. In contrast, quantum mechanics operates in a world where uncertainty, probability, and interconnection replace the certainties of classical physics. It's a realm where the smallest particles of nature are not just influenced by forces, but also by the act of observation itself. Quantum mechanics is both awe-inspiring and humbling. It challenges our deepest intuitions about the world and invites us to reconsider the very nature of reality. As we peer into the subatomic realm, we begin to see a universe more mysterious and strange than we ever imagined a universe governed, not by certainty, but by probability, connectedness, and the wonder of quantum uncertainty. How does our mind interact with the physical world? The mind-body problem has puzzled philosophers, scientists, and thinkers for centuries. How does the immaterial essence of consciousness interact with the physical world? This question lies at the heart of one of the most profound mysteries in the science and philosophy: the relationship between the mind and the body. How does subjective experience, the thoughts, emotions, and awareness we carry within ourselves, come to influence the physical matter that constitutes our body? The interaction of mind and matter remains elusive, and our understanding of this fundamental question shapes not only our understanding of ourselves, but also the very nature of reality itself. At the heart of the mind-body problem is the question of how consciousness affects the physical world. Materialism, the dominant view in modern science, argues that consciousness is the product of physical processes within the brain. According to this perspective, the mind is not separate from the body, but rather a byproduct of it. The firing of neurons, the release of neurotransmitters, and the interactions of molecules in the brain give rise to thoughts, sensations, and self-awareness. From this standpoint, all mental phenomena are reducible to physical process, and there is no need to invoke any mysterious forces or entity. The brain, as a highly complex organ, operates as a machine, and consciousness emerges from its intricate working. Yet, while materialism has given us profound insights into how the brain functions, it leaves an unanswered question: how does the physical brain give rise to the subjective experience of being? This gap in understanding, often referred to as the hard problem of consciousness, highlights the limitations of a purely materialist perspective. The brain can be studied in terms of electrical signals and chemical reaction, but these processes don't explain why we feel something when we think or perceive. Why does the firing of neurons result in the vivid sensory experience of sight, sound, or emotion? Materialism, though powerful in its ability to describe the physical world, fails to account for the richness and immediacy of conscious experience. In contrast to materialism, idealism offers a radically different answer to the mind-body problem. According to idealism, consciousness is not a product of matter. Rather, it is the fundamental essence of reality. From this perspective, the physical world is not independent consciousness, but is rather an expression of. Idealists argue that all that we perceive as matter is, in fact, a manifestation of the mind. The universe, according to this view, is made of ideas, perceptions, and consciousness itself. Idealism does not reduce consciousness to the brain, but sees it as the driving force behind all existence. The world around us, including our bodies, is shaped and defined by consciousness. One of the most famous proponents of idealism was the philosopher George Berkeley, who posited that to be is to be perceived. In this view, objects only exist insofar as they are perceived by a conscious mind. The tree falling in the forest makes no sound if there is no one there to hear it, because, in a sense, the sound doesn't exist without a perceiver to experience. Idealism challenges the materialist view by asserting that mind, not matter, is the primary substance of reality. In this framework, the mind is not just a byproduct of the brain, it is the very essence of everything that exists. While materialism and idealism represent opposite ends of the spectrum, both face challenges when attempting to explain the mind-body interaction. Materialism struggles to explain the nature of subjective experience, while idealism must grapple with how consciousness can create the physical world and how the mind interacts with the material universe. Both philosophies offer compelling insight, yet neither fully solves the puzzle of how consciousness interacts with physical matter. Despite the various theories that seek to explain the mind-body interaction, the mystery remains. How can a non-physical phenomenon like consciousness influence and interact with the physical body? Can the mind control the body, or is it simply a byproduct of it? These questions challenge our understanding of the universe and our place within it. Whether we view consciousness as a product of the brain, the fundamental substance of reality, or something that exists in all matter, the mind-body problem is a puzzle that continues to shape the future of science and philosophy. philosophy. As we look deeper into the nature of consciousness, we may come to realize that the answers to these questions lie not only in the brain or in philosophy, but in the very fabric of existence itself. The mystery of mind-matter interaction invites us to explore the deepest questions about the nature of reality, questions that may one day reveal the true connection between the mind and the cosmos. Could quantum processes in our brain unlock the secrets of awareness? The Orch-OR theory, orchestrated objective reduction, proposed by physicist Sir Roger Penrose and anesthesiologist Dr. Stuart Hameroff, presents one of the most intriguing and controversial ideas about the nature of consciousness. Unlike traditional models that suggest consciousness arises solely from the brain's biochemical processes, Orch-OR introduces a bold proposition that consciousness is rooted in quantum processes occurring within structures inside the brain's neuron, known as microtubule. To understand this theory fully, we must first step away from the familiar materialist view of brain activity and dive into the strange, enigmatic world of quantum mechanics. At the core of the Orch-OR theory is the idea that the brain functions as a quantum computer, with microtubules playing a central role in processing information. Microtubules are microscopic tube-like structures that are a key component of the cytoskeleton of cell. In neurons, they serve a variety of functions, including maintaining cell shape and facilitating intracellular transport. However, according to Penrose and Hameroff, microtubules also provide an ideal environment for quantum computation. In this view, quantum effects specifically, the phenomenon of superposition, are happening inside the microtubule, where they orchestrate the cognitive processes that lead to conscious awareness. But why quantum mechanics? Classical neuroscience has long held that consciousness arises from the activity of neurons and their interaction. In this view, the firing of neurons, the release of neurotransmitters, and the electrical signal traveling through the brain's neural networks are what give rise to our thoughts, feelings, and awareness. However, this explanation fails to address how the subjective experience of consciousness arises from these purely physical interactions, a dilemma often referred to as the hard problem of consciousness, famously articulated by philosopher David Chalmers. This problem challenges scientists to explain how and why the brain's activity creates the vivid, qualitative experience of being aware. Penrose and Hameroff's Orch-OR theory offers a potential solution to this enigma. They propose that traditional neuroscience's focus on neurons and synapses overlooks a deeper quantum level of brain activity. Quantum processes such as superposition, the ability of a quantum system to exist in multiple states simultaneously, and entanglement, the phenomenon where particles become linked in ways that transcend space and time, may provide the foundation for consciousness. In Orch-OR, the collapse of quantum superposition within microtubules is suggested to be the moment when consciousness is orchestrated, when information is processed in such a way that it leads to the emergence of awareness. But why are microtubules the key to this quantum process? Microtubules are unique because of their structural properties. At the quantum level, the geometry and interactions within microtubuli might allow for quantum coherence to persist for longer periods, a phenomenon that is typically difficult to achieve in the warm, noisy environment of the brain. In a typical quantum system, entangled states collapse due to environmental interference, but microtubule, according to Penrose and Hameroff, might act as protectors of quantum coherence. They might allow quantum computations to remain intact long enough to have an impact on brain function and consciousness itself. Penrose, who is known for his work on quantum gravity, also introduced the idea of objective reduction, a process wherein quantum superpositions collapse spontaneously when they reach a critical level of complexity. According to Penrose, the collapse of quantum states may be guided not by the classical mechanics of the brain, but by a deeper physical process governed by the fabric of space-time itself. This suggests that consciousness doesn't just emerge from the interactions of neurons, but from a more fundamental aspect of reality. Contrasting Orch-OR traditional neuroscience, the key difference is that the theory introduces an element of quantum non-locality, a concept that suggests particles can be interconnected in ways that defy classical understanding of space and time. Traditional neuroscience assumes that consciousness is an emergent property of the brain's neural network, evolving over time to provide animals with the ability to process complex information. Orch-OR, on the other hand, places consciousness at the very foundation of the universe, suggesting that quantum processes are not merely a part of the brain's functioning, but an integral component of how the mind interacts with the universe. The idea that consciousness could be a result of quantum processes has far-reaching implications. It not only challenges materialist views, but also opens the door to an entirely new understanding of the mind-body relationship. If consciousness arises from quantum processes within microtubules, it suggests that the mind is not merely confined to the brain, but might extend beyond the physical limits of the body, potentially linking the mind to the universe in ways we are only beginning to explore. Despite its boldness, the Orch-OR theory is not without its critic. Many neuroscientists and quantum physicists argue that the warm, wet environment of the brain is an unlikely place for quantum coherence to persist long enough to influence cognition. Moreover, while microtubules are essential components of cellular structure, there is limited experimental evidence to support the idea that they host quantum computation in the way Penrose and Hameroff suggest. Nevertheless, the Orch-OR theory remains a fascinating attempt to merge quantum mechanics with consciousness and invites new possibilities for understanding the very nature of thought, perception, and reality itself. As science continues to probe the limits of both neuroscience and quantum theory, the Orch-OR hypothesis may one day reveal new pathways toward understanding how consciousness emerges from the intersection of mind and matter, offering answers to one of the most profound questions in human existence. Is our brain a supercomputer powered by quantum magic? The idea that the brain operates like a quantum computer is one of the most mind-bending propositions in the intersection of neuroscience and quantum physics. Traditional computational models view the brain as a highly advanced classical computer, where neurons process information through binary states, much like the ones and zeros of a computer's code. However, the notion of a quantum brain challenges this, proposing that the brain may harness the strange and powerful principles of quantum mechanics, such as superposition and entanglement, to perform computation far beyond the capabilities of classical systems. At the heart of this idea is the concept of quantum computation, a type of computation that operates on quantum bits, or qubits, rather than classical bits. While a classical bit can represent a state of either 0 or 1, a qubit can exist in a superposition, simultaneously representing both 0 and 1. This ability to process multiple states at once gives quantum computers an immense advantage when solving certain types of problems, such as factoring large numbers or simulating complex molecular structures. The question then arises, if the brain is indeed a quantum computer, could it be exploiting these very properties, superposition and entanglement, to process information in ways we have yet to fully understand? Superposition allows a quantum system to exist in multiple states at the same time. In the context of a quantum computer, this means that a qubit can represent a combination of both 0 and 1 until it is measured, at which point it collapses into a definite state. Imagine trying to solve a puzzle with multiple possible answers. A classical computer would check each possibility one by one, whereas a quantum computer could explore all the possibilities simultaneously, greatly speeding up the process. In theory, the brain could be using superposition to perform parallel processing at a scale and speed that classical computing cannot match. Instead of considering only one solution at a time, the brain could hold multiple potential answers in a superposition of state, collapsing into a final solution when needed. Entanglement, another hallmark of quantum mechanics, refers to the phenomenon where two or more quantum particles become linked, such that the state of one particle instantaneously influences the state of the other, regardless of distance. In a quantum computer, this allows for highly efficient information transfer, as entangled qubits share information without the need for traditional data transmission. Applying this concept to the brain, some theorists propose that quantum entanglement could explain how different regions of the brain are able to communicate and synchronize with one another so efficiently. Entanglement might enable instantaneous and coherent coherent connections between neurons, allowing for complex cognitive processes such as consciousness, perception, and decision-making to emerge from the coordinated activity of the brain's neural network. The possibility that the brain functions as a quantum computer raises exciting potential for understanding how the mind works. Traditional neuroscience has long emphasized the brain's neural networks as the primary agents of cognition. Neurons communicate through electrical impulses and neurotransmitters, transmitting information across synapses to other neurons. However, this classical view doesn't fully explain the complexity and richness of conscious experience. The brain, in this light, might be more than just an electrochemical system. It could be a quantum system capable of exploiting quantum mechanics to process vast amounts of information simultaneously and in ways that classical computers simply cannot replicate. The contrast between classical computation and quantum computation is fundamental in understanding how a quantum brain might operate. In classical computation, operations are deterministic. Each step follows from the previous one, and the state of the system is well defined at any point in time. Classical systems are bound by limitations of speed and complexity, as they can only process one state at a time. However, quantum computers break free of these limitations by operating probabilistically. They harness the power of quantum superposition to explore many possible outcomes at once, and the phenomenon of quantum entanglement to connect distant parts of the system in ways that classical computing cannot replicate. This computational advantage could be a crucial factor in the brain's ability to process information efficiently and creatively. For example, if the brain were a quantum computer, it might have the ability to solve problems in real time that would take classical computers much longer to process. This could explain the human brain's remarkable ability to think, adapt, and make decisions based on incomplete or contradictory information. It could also account for the rapid integration of sensory data, emotional responses, and abstract reasoning that gives rise to conscious thought. However, the idea of the brain functioning as a quantum computer is not without its critics. Some scientists argue that the warm, wet environment of the brain is an unlikely candidate for supporting the delicate quantum processes necessary for quantum computation. Quantum systems are notoriously sensitive to their surroundings, and it is difficult to maintain quantum coherence, where quantum states are preserved over time in a biological system. Despite this, recent advances in quantum biology have uncovered evidence suggesting that quantum processes may indeed play a role in biological systems, particularly in processes like photosynthesis and bird navigation. These findings have led some researchers to reconsider the possibility of quantum computations in the brain. While the idea of a quantum brain remains speculative, it offers an exciting new avenue of exploration. If the brain does operate as a quantum computer, it would not only redefine our understanding of consciousness, but could also revolutionize fields ranging from artificial intelligence to cognitive neuroscience. The notion that the mind operates on quantum principles challenges our deepest assumptions about the nature of reality and suggests that the brain may tap into a fundamental aspect of the universe to process information in ways we have yet to comprehend. What holds our thoughts together in a single moment? One of the most fascinating aspects of quantum mechanics is the concept of quantum coherence, which refers to the ability of particles to maintain a synchronized quantum state over time. In the macroscopic world, this coherence is typically fragile and tends to break down rapidly, an occurrence known as decoherence. But what if quantum coherence plays a role in explaining consciousness itself, particularly the unity of consciousness? This idea challenges the traditional view of consciousness as a product of localized classical brain activity and suggests that our conscious experience might emerge from quantum coherence within the brain. Quantum coherence is a phenomenon where the quantum states of particles, such as electrons or photons, remain in a well-defined interdependent state. This means that different parts of a quantum system can be in a superposition where each part is linked together in a coherent whole. In simple terms, when quantum coherence is maintained, different particles can influence each other across distances, creating a unified, holistic system. For instance, when a quantum computer operates, qubits are in a state of coherence, allowing them to perform complex calculations simultaneously. Without coherence, the quantum advantages of superposition and entanglement would disappear, and the system would revert to classical behavior. This notion of coherence may be key to understanding consciousness. Classical neuroscience suggests that consciousness arises from the complex interactions of neurons in the brain. These neurons, firing and transmitting signals, form a network that allows us to process information, make decisions, and perceive the world. However, this view fails to explain why all of this activity feels like a unified experience. The feeling of being one person experiencing time, space, emotions, and thoughts as part of a cohesive whole is difficult to account for in purely classical terms. This is where quantum coherence might step in. The Orch-OR theory, proposed by Penrose and Hameroff, suggests that the brain may harbor quantum coherence within its microtubule, tiny structures within neurons that play a critical role in cellular organization. These microtubules could be capable of maintaining quantum states long enough to influence brain activity. In this scenario, the unity of consciousness could be the result of quantum coherence across the brain's neural network. Just as the particles in a quantum system are entangled and interdependent, the conscious experience might emerge from a network of quantum processing, providing a seamless integration of information across different regions of the brain. But why does this idea of quantum coherence matter for consciousness? The key lies in the fact that our conscious experience is not a series of disjointed thoughts, feelings, and perceptions, but a unified flow of awareness. When we perceive an object, hear a sound, or feel an emotion, these experiences are not isolated. They are intricately woven together into a single, cohesive awareness. This unity of experience suggests that there must be some underlying mechanism that integrates the different components of consciousness. Quantum coherence could provide this mechanism by enabling different parts of the brain to work together as a whole despite their physical separation. In contrast, decoherence occurs when quantum systems interact with their environment in such a way that their quantum states break down into classical behavior. This is typically seen in macroscopic systems, where the interaction with the environment causes the delicate quantum states to collapse into definite, observable outcomes. Decoherence is why we don't see everyday objects behaving in a quantum manner. Objects like cars, trees, and even our bodies interact with their surroundings in ways that cause quantum coherence to dissipate. In the macroscopic world, things appear separate, independent, and predictable, following the deterministic laws of classical physics. The brain, being a warm, wet environment, is thought to be particularly prone to decoherence. The constant activity of neurons and the interactions of molecules make it difficult for quantum state to remain coherent for long periods of time. Yet the Orch-OR theory suggests that the microtubules in neurons provide a special environment where quantum coherence might persist long enough to play a role in consciousness. In this way, quantum coherence in the brain could explain the phenomenon of unity, how diverse aspects of sensory perception, thought, and emotion are integrated into a single, cohesive experience. The contrast between coherence and decoherence highlights the challenges of maintaining quantum states in biological systems. While decoherence typically governs large macroscopic systems, quantum coherence is thought to be fragile and short-lived in the brain's environment. However, Penrose and Hameroff's theory posits that the microtubule might protect quantum coherence, allowing it to persist long enough to influence brain function and lead to the emergence of consciousness. If this is true, then the brain is not merely a classical computing system, but a quantum processor capable of maintaining coherence at the level of the mind. This idea holds profound implications for our understanding of consciousness. If quantum coherence is involved, it suggests that consciousness may not be a purely emergent property of the brain's neural activity. Instead, it could be a deeply integrated, fundamental aspect of reality tied to the very nature of quantum physics itself. Consciousness might not simply arise from the brain's activity, it could emerge from the interplay between quantum coherence, the brain, and the universe. Ultimately, the role of quantum coherence in consciousness remains speculative, but it offers a bold new lens through which to examine the mind. By exploring how quantum states might influence the brain's process, we could be on the verge of unlocking new understandings of how and why we experience consciousness as a unified whole. The balance between quantum coherent and decoherent might be central to how the brain generates consciousness. Coherence allows for the holistic integration of brain function, while decoherent might provide the necessary separation between distinct cognitive processes, preventing interference and ensuring proper functioning. The interplay between these two states, quantum coherence enabling unity and decoherence ensuring classical stability, could be the key to unlocking the mystery of consciousness and how it emerges from the brain's intricate processes. Can thoughts travel faster than light through hidden connection? Quantum entanglement is one of the most mysterious and intriguing phenomena in quantum mechanics. It refers to the phenomenon where two or more particles become linked in such a way that the state of one particle instantaneously influences the state of the other, regardless of how far apart they are. This non-local connection challenges our classical understanding of space and time, suggesting that information can travel across vast distances instantaneously. While entanglement is often discussed in the context of subatomic particles, it also offers a fascinating potential explanation for how the brain might process information in ways that classical models cannot easily account for. In classical physics, communication between 2 points occurs through signals that travel through space, typically at the speed of light. This means that information is always limited by the speed of the medium through which it is transmitted. For example, when a neuron transmits an electrical signal across a synapse to another neuron, the signal moves at a finite speed, taking time to travel from one point to the next. The brain's ability to process information is thus constrained by these classical limits, electrical signals traveling through neural networks one step at a time. This model works well for many aspects of brain function, but it may not fully account for the brain's capacity to handle highly complex synchronized processes, particularly when it comes to consciousness and cognitive integration. This is where quantum entanglement presents an exciting possibility. In a quantum system, entangled particles do not communicate through signals that travel through space. Instead, their states are directly connected in a way that transcends distance and time. When two particles become entangled, their properties, such as their spin, polarization, or position, are linked in such a way that changing the state of one particle will instantaneously affect the other, regardless of how far apart they are. This instantaneous connection does not rely on conventional communication, and its effects seem to occur faster than the speed of light, defying classical notions of causality. In the context of the brain, some researchers have speculated that quantum entanglement could be responsible for the synchronization of neural activity across different regions of the brain. The brain is known for its ability to integrate complex information from various sources: sensory input, memory, emotions, and reasoning, all of which must be processed simultaneously to create a unified experience of consciousness. However, this integration is not always easy to explain in classical terms. For instance, when we make decisions, we are often drawing on multiple pieces of information from different brain regions. Yet, we experience this process as a seamless flow of thought, as though our entire brain is working together as one unified system. Could quantum entanglement be the key to this phenomenon? If certain brain regions are entangled at the quantum level, it could allow for instantaneous communication between distant parts of the brain, enabling the synchronized processing of information across vast neural networks. This would provide a more efficient mechanism for integrating complex cognitive processes such as perception, emotion, and memory into a cohesive conscious experience. The entangled brain regions could communicate with one another in real time, without the time delays that occur with classical neuron-based communication. This quantum synchronization might explain how the brain can process and integrate information so quickly and efficiently, contributing to the seamless flow of conscious thought. Furthermore, quantum entanglement might also help explain how the brain manages to process information in parallel. Classical neural communication typically occurs in a sequential manner, with one neuron firing after another. However, quantum entanglement allows for the possibility of parallel process across different regions of the brain. As entangled untangled neuron could exchange information simultaneously rather than in a step-by-step manner. This would offer a computational advantage, enabling the brain to perform complex tasks much faster than a purely classical system could. For example, it could explain how we can simultaneously process multiple streams of sensory input, such as sight and sound without delay, allowing us to react to the environment in real time. Of course, the idea that the brain could leverage quantum entanglement to process information is still highly speculative, and many challenges remain in validating this hypothesis. One of the key obstacles is that quantum coherence needed for entanglement to occur tends to break down rapidly in the warm, noisy environment of the brain. The delicate quantum states that underlie entanglement are highly sensitive to environmental interference, and maintaining them in the brain's biological system presents a significant hurdle. Some researchers argue that the brain's structure, particularly microtubules, could provide a unique environment that supports quantum coherence and entanglement long enough for it to have an impact on cognition. However, this idea remains controversial, and further research is needed to determine whether quantum entanglement can truly play a role in brain function. In contrast to classical communication, where signals travel through space and time, quantum entanglement offers the potential for instantaneous and non-local communication. This ability to link distant parts of the brain in a coherent, synchronized manner could open up new possibilities for understanding how the brain processes complex, integrated information. While much of this remains theoretical, the idea of quantum entanglement in the brain suggests that consciousness might not be a product of classical neural activity alone, but rather a deeply interconnected phenomenon that harnesses the strange and powerful principles of quantum mechanics. As scientists continue to investigate the role of quantum mechanics in the brain, quantum entanglement remains a key area of exploration. It could provide a fascinating bridge between the mind's remarkable capacity for complex processing and the fundamental principles of quantum physics that govern the universe. Is your mind connected to the star? The concept of consciousness has long been seen as an inward experience, product of the brain's complex neural networks confined within the boundaries of the physical body. However, an emerging and increasingly intriguing idea suggests that consciousness may not be solely a localized phenomenon, but a conduit, enabling us to interact with the universe at a quantum level. This perspective opens up a fascinating possibility that our minds may not be isolated entities, but rather interconnected with the fabric of the universe itself. Could consciousness be the bridge that connects our individual experiences to the larger quantum reality that surrounds us? At the heart of this idea is the recognition that the brain is not just a machine processing information within its own biological system. Instead, the brain may function as a receiver or transceiver of information from the universe, tapping into quantum processes that go beyond the immediate confines of the body. In this view, consciousness becomes more than just the output of neural activity. It becomes a dynamic interface capable of perceiving and interacting with the fundamental forces that govern the cosmos. Quantum mechanics, with its strange and often counterintuitive principles, provides a potential framework for understanding this connection. Concepts like entanglement, superposition, and non-locality suggest that at the most fundamental level of reality, everything in the universe is interconnected. These quantum phenomena seem to transcend the classical distinctions of space and time, indicating that particles and systems can be linked in ways that defy our traditional understanding of physical distance and causality. If the brain can tap into this quantum, consciousness may act as a bridge, linking the individual mind to the universal web of existence. This idea contrasts with traditional materialist views of the brain, which see consciousness as emerging purely from local brain function. In classical neuroscience, consciousness is thought to arise from the intricate network of neuron, electrical impulse, and biochemical reactions within the brain. These processes are thought to be isolated within the skull, with the brain's activity limited to the realm of the body. While this view has provided valuable insight into how we process sensory information, think, feel, it falls short when trying to explain the profound, interconnected nature of human consciousness. Take, for example, the concept of unified awareness. When we experience a thought, feeling, or sensory perception, we don't perceive them as fragmented pieces of information. Instead, we experience them as a seamless flow of consciousness. This sense of unity seems to point to something greater than the sum of individual neural processes. If consciousness were only a product of local brain activity, why would we experience it as a cohesive whole? Could the answer lie in the brain's ability to interact with quantum processes that are deeply woven into the structure of the universe? In contrast to the local, isolated nature of brain function, universal interconnectedness is a core principle of quantum physics. The famous phenomenon of quantum entanglement, for instance, reveals that particles can become linked in such a way that a change to one particle will instantaneously affect the other, no matter how far apart they are. This suggests that at the quantum level, the universe is far more interconnected than we experience in our everyday life. If consciousness is somehow connected to this quantum, it might allow us to tap into a deeper, universal network that extends far beyond the confines of the body. Philosophers and quantum theorists have speculated that consciousness could be the key to understanding this deep interconnectedness. Panpsychism, example, suggests that consciousness is not an isolated phenomenon, but a fundamental quality inherent in all matter. If this is the case, then our brains may not be creating consciousness from scratch, but rather acting as filters, allowing us to perceive and interact with a universal consciousness that is woven into the very fabric of reality. This idea proposes that consciousness is not confined to individual minds, but is a shared, collective experience that connects all things. Furthermore, quantum mechanics suggests that information is not bound by space and time in the way classical physics dictate. The concept of non-locality means that information can exist across vast distances, not confined to the traditional rule of space. If the brain can access this non-local information, it could explain why we sometimes experience flashes of insight, intuition, or inspiration that seem to come from beyond our immediate surroundings or knowledge. This type of perception could be our consciousness tapping into a deeper, universal information network, one that transcends time and space, linking us to the cosmos in ways we don't fully understand. This bridge between consciousness and the universe raises profound questions about the nature of reality itself. Is the mind simply a byproduct of neural activity, or does it play a more significant role in the unfolding of the universe? Could our awareness be a part of a larger cosmic consciousness where individual minds are like nodes in a vast, interconnected network? The exploration of these ideas invites us to rethink our place in the universe, not as isolated beings, but as part of a dynamic, interconnected system that extends beyond the limits of the physical world. In the end, the idea of consciousness as a bridge to the universe challenges our understanding of both the mind and the cosmos. By proposing that our consciousness might connect us to the deeper, quantum fabric of reality, this theory opens up new possibilities for understanding the mysteries of the mind and the universe itself. Whether or not we can ever prove this connection, the idea itself offers a tantalizing glimpse into the profound interdependence of mind, matter, and the cosmos. Is the universe a hologram? And is our mind its projector? The holographic principle, first proposed in the context of black hole physics and cosmology, offers a radically new way of understanding the universe. At its core, this idea suggests that the universe may not be as it seems what we perceive, as three-dimensional space could be an illusion, holographic projection from a two-dimensional surface. This theory, which originated in attempts to understand the paradoxes of black hole entropy, posits that all the information contained within a region of space can be encoded on its boundary, much like how a hologram encodes three-dimensional information on a two-dimensional surface. At first glance, this might sound like pure science fiction, but the holographic principle is supported by some of the deepest insights in modern theoretical physics, particularly in the study of black holes and string theory. According to physicists such as Juan Maldacena, the universe could be a kind of hologram, where the reality we experience, our three-dimensional universe, is actually a a projection from information encoded at the boundary of space-time. In this sense, the universe could function like a giant cosmic hologram, where the entirety of the cosmos is encoded in two-dimensional form on a distant surface, with the information unfolding in our three-dimensional world as an image, much like a 3D object appearing from a 2D hologram. Now imagine how this concept might apply to consciousness. Just as the holographic principle suggests that the physical universe may be a projection from a deeper two-dimensional surface, could consciousness itself function similarly, emerging from a deeper hidden layer of reality encoded in the brain? Neural activity? If the brain were in some sense a holographic projector, then the mind, much like the universe, could be a projection of deeper underlying. This idea may sound abstract, but it provides an intriguing analogy to the way we experience reality as a conscious, unified whole. Even though the brain is composed of discrete individual neurons firing and communicating in a complex network. In a hologram, every part of the image contains information about the whole. Similarly, consciousness might not be localized in just one part of the brain, but instead be a distributed phenomenon, with each part of the brain contributing to a unified experience. This would contrast with traditional, localized models of brain function, which suggest that specific areas of the brain are responsible for specific aspects of cognition. Instead, if consciousness were holographic, it could be that every part of the brain contains the whole. That is, every neural network and every neuron could be a reflection of the entire conscious experience. The relationship between physical space, the three-dimensional world we interact with daily, and the holographic representation of reality proposed by the holographic principle invites a fascinating thought experiment. What if the brain itself is also functioning in a way that's fundamentally different from classical models? Instead of perceiving the world as a linear, step-by-step sequence of inputs and outputs, the mind might process and experience it as a projection, much like how a hologram forms a three-dimensional image from flat surfaces. This analogy could help explain certain paradoxes of consciousness. For instance, how do we experience the world as a unified, cohesive stream of awareness when the brain processes information in fragmented, localized parts? The holographic principle suggests that the whole of consciousness may be encoded in each part of the brain, and thus our experience of a coherent self might arise from a network of distributed information. This echoes some quantum mechanical ideas, where non-locality and entanglement suggest that information is not confined to specific location, but is spread out across the system as a whole. Just as every part of a hologram contributes to the full image, every part of the brain might contribute to the full experience of being conscious. Furthermore, the idea of the universe as a hologram also challenges our conventional understanding of space and time. If the universe is a projection, then what we perceive as three-dimensional space might not be fundamental, but rather a manifestation of deeper, underlying information. In a similar vein, consciousness might not be a product of the brain's physical activity alone, but a manifestation of deeper informational process, possibly linked to quantum mechanics or some form of universal consciousness. The brain, in this framework, becomes not just a receiver and processor of sensory information, but a projector of consciousness, interpreting and making sense of this deeper layer of reality. In this context, the physical brain might be seen as the boundary from which consciousness emerges, much like how the surface of a black hole's event horizon encodes all the information within. Our subjective experience of the world, the feeling of being here in space, perceiving objects, thinking thoughts, and making decisions, could be a projection of a deeper, more fundamental reality encoded within the brain's neural activity, but extending far beyond it in ways we do not yet fully understand. The holographic principle invites us to reconsider the relationship between the mind, the brain, and the universe itself. Just as the universe may be a holographic projection, could our consciousness be similarly projected from deeper, quantum-level information? Could the brain, acting as a holographic projector, be the means through which we connect to this deeper layer of reality? These These questions point to a deeper interconnectedness between mind and cosmos, offering profound implications for our understanding of both consciousness and the universe. Does observing change everything? The observer effect is one of the most famous and perplexing phenomena in quantum mechanics. It refers to the idea that the act of observing or measuring a quantum system can alter state. This principle is famously illustrated by experiments such as the double-slit experiment, where particles like electrons or photons behave differently when observed as compared to when they are left unobserved. When not being measured, these particles seem to exist in a state of superposition, where they can be in multiple states at once. However, the moment they are observed, they collapse into a single state, as though the act of observation has influenced their reality. This peculiar behavior has led many to wonder, could consciousness itself play a fundamental role in shaping the reality we experience? The observer effect in quantum mechanics suggests that the presence of an observer is essential in determining the outcome of certain events at the quantum level. This idea runs counter to the classical notion of reality, where things exist independently of being observed. In the quantum realm, it seems as though reality is not fixed until it is observed or measured. This leads to a fascinating question. Does consciousness, as the ultimate observer, play a role in determining the physical world around us? Could the very act of observing create the reality we experience? This hypothesis, often referred to as the consciousness causes collapse theory, suggests that consciousness itself might be responsible for collapsing the wave function, the probabilistic superposition of all possible states into a definite outcome. The classic interpretation of quantum mechanics, known as the Copenhagen interpretation, proposes that the act of measurement forces a quantum system to choose one state from a multitude of possibilities. However, the role of the observer has yet remained a mystery. While many physicists suggest that the observer need not be conscious, merely an interaction with a measuring device, it is still an open question whether the consciousness of the observer could be a deciding factor in this process. If consciousness does play a role in creating reality, it would challenge our traditional understanding of the world. The passive observation model suggests that consciousness simply receives information, observing a reality that already exists independently of it. However, if consciousness is actively involved in creating reality, then it would imply that our minds are not merely passive receivers of sensory input, but active participants in shaping the universe. This would suggest that reality is not a static, objective entity, but a dynamic participatory process shaped by the interaction between consciousness and the quantum field. This active creation of reality contrasts sharply with the traditional materialistic view that the universe exists independently of consciousness. In classical physics, the universe is governed by deterministic law, with objects existing and behaving according to predictable patterns, regardless of whether anyone is observing. In this view, consciousness is simply a byproduct of brain activity, a passive observer of a pre-existing reality. However, the observer effect in quantum mechanics opens up the possibility that consciousness may be more than just an observer. It might be a creator of the very fabric of reality. The implications of this theory are profound. If consciousness is involved in collapsing the wave function and thus creating reality, it would suggest that the world around us is not as fixed and objective as we perceive it to be. Instead, it would point to a universe that is co-created by the observer and the observed, where each individual mind plays a part in shaping the world it experiences. This could mean that our perceptions, thoughts, and intentions have a direct influence on the physical world, opening up possibilities for phenomena like mind over matter or the power of intention. This view also aligns with certain philosophical and spiritual traditions, which have long held that consciousness is not simply a passive reflection of the external world, but an active force that shapes reality. In many Eastern philosophy, for example, the mind is seen as intricately connected to the fabric of the universe, with thought and perception directly influencing the external world. The observer effect in quantum mechanics might offer a scientific parallel to these ancient teachings, suggesting that the mind and the universe are deeply interconnected, with consciousness playing an active role in the creation of the world. On the other hand, there is the many worlds interpretation of quantum mechanics, which argues that all possible outcomes of a quantum event occur, but in separate, non-interacting branches of reality. This interpretation removes the need for a conscious observer to collapse the wave function, suggesting that the universe exists independently of the observer's consciousness. While While this view negates the idea of consciousness directly shaping reality, it also points to the richness and complexity of the quantum world, where multiple realities can coexist simultaneously. In conclusion, the observer effect raises profound questions about the relationship between consciousness and reality. If consciousness plays an active role in creating the reality we experience, it would challenge our traditional views of a detached, objective universe. Instead, it suggests a universe where reality is shaped through the active participation of conscious beings, blurring the line between observer and creator. Whether consciousness is merely a passive observer or an active participant in the creation of reality, quantum mechanics forces us to reconsider our place in the universe and the true power of the mind. As we delve deeper into the mysteries of quantum mechanics, we may find that consciousness itself is not just a spectator, but a creator of the universe we inhabit. According to quantum theory, particles exist in a superposition of state, meaning they can be in multiple positions or states at once until measured or observed. The act of observation seems to force the particle to choose a specific state, but the precise mechanism behind this phenomenon remains unclear. Some interpretations of quantum mechanics suggest that consciousness itself might play a pivotal role in this collapse. The idea that consciousness is necessary for the collapse of the wave function challenges the conventional understanding of quantum mechanics, which typically treats measurement as a physical process, independent of human observation. At the heart of quantum mechanics is the concept of superposition, the idea that quantum particles like electrons or photons do not have definite properties until they are observed. In the double-slit experiment, for example, particles behave as though they are in two places at once, creating an interference pattern when not measured. However, once a measurement is made, the particle collapses into a single, defined state. This is the core of what is known as the wave function collapse, the transition from a superposition of multiple possibilities to one definite outcome. The question then arises, what causes this collapse? Why does the wave function collapse into a definite state when observed and not before? The Copenhagen interpretation, one of the most widely accepted views of quantum mechanics, proposes that the wave function collapse occurred due to measurement, but it doesn't clarify whether it is the physical act of measurement or something else such as consciousness that causes this change. In this framework, when an observer interacts with a quantum system, the system's probabilistic states collapse into a single reality. But is the observer simply a passive entity, or does consciousness actively participate in this process? The consciousness causes collapse hypothesis posits that the act of conscious observation is required to collapse the wave function. According to this interpretation, the quantum world remains in a state of superposition until a conscious observer makes a measurement, which forces the wave function to collapse into a single state. This idea was famously explored by Werner Heisenberg and later expanded by John von Neumann, who suggested that the process of measurement in quantum mechanics is inseparable from the consciousness of the observer. In this view, consciousness does not just passively observe reality, it actively shapes it. This controversial concept implies that consciousness might be intimately tied to the fabric of reality, as if the mind is not just a bystander, but a participant in the creation of the universe. According to proponents of this theory, the mere presence of a conscious observer is what gives rise to the definitive reality we experience. Without an observer, the universe remains in a state of potentiality, where all possibilities exist simultaneously, and reality as we know it is not fully real until it is perceived by a conscious mind. The idea that consciousness is required to collapse the wave function presents a stark contrast to deterministic views of quantum mechanics. In traditional interpretations of quantum theory, such as the many-worlds interpretation, the wave function does not collapse at all. Instead, all possible outcomes of a quantum event occur, but in separate, non-interacting branches of reality. This view eliminates the need for an observer to collapse the wave function, instead suggesting that the universe splits into multiple realities every time a quantum event occurs. Here, the observer is irrelevant to the collapse process, and the universe continues in a deterministic manner, with every possibility playing out simultaneously. By contrast, the idea that consciousness causes the collapse of the wave function implies a non-deterministic universe. If the act of observation by a conscious mind is necessary to collapse the wave function, then the outcome of quantum events is not predetermined. Rather, it suggests that the future is not fully determined. by past states, but is in some way shaped by conscious observation. This viewpoint opens up the possibility that consciousness is not merely a passive receiver of information, but an active participant in the unfolding of reality itself. In this framework, the universe might be fundamentally interconnected with consciousness, where the observer does not just observe, but helps bring the physical world into being. Critics of the consciousness causes collapse hypothesis argue that this interpretation overemphasizes the role of consciousness, and that measurement itself is a physical process that does not require a conscious observer. Some proponents of the decoherence theory assert that the interaction between a quantum system and its environment is enough to cause the collapse of the wave function without the need for conscious observation. According to this view, 1. A quantum system interacts with its environment. It becomes entangled with the environment, and the superposition is effectively lost to the classical world, resulting in a definite outcome. Here, the collapse is a result of physical processes, not consciousness. However, the persistent mystery of how the wave function collapses and why consciousness seems to play a special role suggests that we may still be on the verge of a profound understanding of both quantum mechanics and the nature of consciousness. Could consciousness be the missing link in our understanding of reality, the force that turns potentiality into actuality, or is the act of measurement simply a feature of quantum mechanics independent of consciousness itself? In the end, the relationship between consciousness and the wave function collapse remains one of the most fascinating questions in modern physics, challenging our understanding of both the mind and the universe. As we continue to explore the quantum world, we may come to realize that the answer lies not in the particles themselves, but in the minds that observe them. Is reality just what we make of it? What if the reality we experience, our perception, thought, and feelings, is not just a passive reflection of an objective world, but instead a quantum phenomenon? This perspective suggests that our subjective experience of reality might be influenced by the very principles of quantum mechanics. Whereas classical physics posits that an objective reality exists independently of observation, quantum mechanics introduces the idea that the act of observing itself influences what we perceive. This opens up the possibility that the world we experience could be as much a product of our consciousness and perception as it is a reflection of an external physical reality. In classical terms, the world is often seen as a collection of fixed objects governed by predictable deterministic law. The universe exists whether or not we observe it, and our role as observers is seen as passive. We simply receive sensory information about an external world that exists independently of us. However, quantum mechanics complicates this view. In quantum theory, particles exist in a superposition of states both here and there, or both up and down until they are observed. It's the act of observation that forces these multiple possibilities to collapse into one definite outcome. This suggests that reality, at its most fundamental level, might not be as fixed and objective as we once thought. Instead, it could be deeply tied to the process of observation itself, including the subjective perception of those observing it. The idea that our perception of reality is shaped by quantum processes contrasts sharply with the classical notion of an objective reality that exists independent of us. According to classical physics, the universe operates according to unchanging laws, whether or not anyone is around to witness. In this view, perception is simply the brain's interpretation of this objective reality, processing sensory input from the external world. However, quantum mechanics challenges this objective framework by suggesting that reality may be more fluid, dependent on the interaction between the observer and the observed. The quantum realm introduces the idea that consciousness, our awareness, and perception could play a role in shaping the world we experience. This perspective opens up new possibilities for understanding the personalized nature of perception. Every individual's experience of reality may not be a direct reflection of an objective world, but rather a subjective construct, influenced by the observer's consciousness. Just as the act of observation collapses the wave function into a single outcome, the brain might collapse a vast array of sensory inputs and possibilities into the coherent, unified reality we experience as conscious being. In this sense, reality is not a fixed external truth, but a constantly evolving experience shaped by our perceptions and choices. Take, for example, the way we perceive the color of an object. Classical physics would tell us that the color of an object, such as a red apple, is an objective property of the apple, independent of the observer. However, quantum theory suggests that our perception of the apple's color might be a subjective experience, influenced by the unique neural and cognitive process of the observer. Our perception of the apple's red could be a result of the interaction between the external world and the brain's interpretation of it, a subjective, personalized experience that is different for each individual. In quantum mechanics, the principle of non-locality suggests that particles are interconnected in ways that defy classical understanding. Could this interconnection extend to the brain and its conscious processes, allowing for a deeper connection between the mind and the universe? If our subjective experience is influenced by quantum processes, it might imply that we are not separate from the world around us, but instead deeply connected to it. Our perception of the world might be a manifestation of a deeper, more fundamental reality, one that is not bound by the limitations of space and time, but instead shaped by quantum entanglement and interconnectedness. This brings us to the idea of personalized reality. If our consciousness plays an active role in shaping the world we experience, then each individual's reality might be unique, filtered through their own perceptions, memories, and cognitive processes. This aligns with certain philosophical ideas, such as idealism, which suggests that reality is not external to the mind, but rather constructed within it. From this perspective, what we perceive as the external world is, in fact, a projection of our consciousness, influenced by our mental processes and the underlying quantum mechanisms that shape our perception. The subjective nature of experience also raises questions about the nature of objective reality itself. If quantum mechanics suggests that observation plays a fundamental role in shaping what we perceive, can we ever truly know the objective reality of the universe, independent of our consciousness? Perhaps our experience of reality is not just a reflection of the world, but an active creation of it, a co-production between the mind and the universe at the quantum level. This could explain why different people might have different perceptions of the same event or object. Reality, in this sense, might not be a fixed, universal truth, but a personalized experience shaped by both external force and internal consciousness. In conclusion, the idea that our subjective experience of reality is a quantum phenomenon challenges the traditional notion of an objective, independent universe. Instead, it suggests that the world we experience is deeply interconnected with our consciousness, shaped by quantum processes such as superposition, entanglement, and observation. If consciousness plays a role in collapsing the wave function and creating reality, it means that our perception of the world is not merely a passive reception of information, but an active and personalized experience. In this light, the boundaries between mind and universe blur, suggesting that the reality we live in may be as much a product of consciousness as it is a reflection of the physical world. Is consciousness everywhere, even in a rock? The cosmic mind, is the universe conscious? One of the most profound and daring ideas in the philosophy of mind is panpsychism, the notion that consciousness is not confined to humans or animals, but is a fundamental quality of the entire universe. In other words, panpsychism proposes that consciousness is intrinsic to all matter, not something that emerges solely from complex biological systems like the human brain. From this perspective, everything in the universe, from the smallest particle to the largest galaxies, possesses some form of consciousness or experience. While this may sound outlandish at first, panpsychism offers a radically different way of looking at the relationship between consciousness and the physical world. At its core, panpsychism challenges the materialist worldview, which has dominated scientific and philosophical thought for centuries. Materialism asserts that everything in existence, including consciousness, can be explained by physical process alone. According to this, consciousness is a byproduct of the brain's complex neural activity, emerging only when certain physical conditions are met, typically in higher organisms like human. In contrast, panpsychism suggests that consciousness is not a mere product of physical interactions, but a fundamental property of all matter. Just as mass or energy is intrinsic to physical objects, consciousness may be an inherent aspect of reality, woven into the fabric of the universe itself. This idea is not entirely new. Philosophers such as Galen Strawson and Philip Goff have championed panpsychism as a potential solution to the hard problem of consciousness, the question of how subjective experience arises from physical matter. If consciousness is truly a fundamental aspect of the universe, panpsychism offers a compelling explanation for why conscious experience exists in the first place. Rather than seeing consciousness as something that emerges from a certain level of complexity in the brain, panpsychism suggests that consciousness is present in all things, though in varying degrees of complexity and intensity. One of the most appealing aspects of panpsychism is its potential to bridge the gap between the subjective and the objective. Traditional materialist theories struggle to explain how subjective experiences, how it feels to be you or me, can emerge from purely physical process. Even the most sophisticated neural networks, with their complex interactions of neurons and synapses, don't seem to offer a satisfactory answer to why or how we have personal, qualitative experience. Panpsychism sidesteps this dilemma by positing that consciousness is not something that suddenly emerges in human, but is a property of all matter with varying degrees of complexity. According to this view, even the simplest particles may have rudimentary forms of experience, though not the full richness of human consciousness. If consciousness is truly everywhere, then the universe is not a dead, indifferent place, as materialism suggests, but a vast, interconnected system where every part has some degree of awareness. For example, rather than viewing a rock as an inert, unconscious object, panpsychism would assert that the rock might possess a form of consciousness, albeit vastly different from human awareness. The rock's consciousness would be fundamentally different from ours, not a conscious experience of thoughts and feelings, but perhaps a more primitive form of awareness tied to its existence and interactions in the world. The same could be said for plants, animals, and even fundamental particles like electrons and quarks. Each of these, under panpsychism, could have a rudimentary form of consciousness with its own subjective experience, however basic it may be. This view contrasts sharply with materialism, which holds that consciousness arises only in complex systems, particularly biological organisms like human. According to materialism, consciousness is something that emerges from the intricate computations and interactions of neurons in the brain. In this view, once we understand the neural correlates of consciousness, we can fully explain its nature. But as appealing as this idea may sound, it raises a critical question. How do neurons firing in the brain give rise to the rich, subjective experiences that we call consciousness? Materialism is often criticized for not adequately addressing this question, the so-called hard problem of consciousness. Panpsychism, by contrast, offers a solution. If consciousness is fundamental, there is no need to explain its emergence. It's simply part of the fabric of reality. One objection to panpsychism is that it appears to attribute consciousness to things that seem obviously non-conscious, like rocks or particles. How can something as simple as an electron have subjective experience? Proponents of panpsychism argue that consciousness does not require the complexity and organization of the brain. Instead, consciousness might be a fundamental property that exists in a rudimentary form in all matter. It doesn't necessarily mean that electrons have the same kind of awareness we do, but rather that they possess a primitive form of experience, one that becomes more complex as matter organizes itself into higher forms, such as animal, human. The implications of panpsychism are far-reaching. If consciousness is indeed a fundamental feature of the universe, it means that everything in existence, every atom, every molecule, every star, is in some sense conscious. This perspective radically alters our understanding of the universe, suggesting that it is not a cold, lifeless system of physical laws, but a vibrant, interconnected web of conscious experience, where all parts contribute to the whole. Such a view aligns with certain spiritual and mystical traditions which have long held that consciousness pervades all of existence, binding everything together in a web of awareness. In conclusion, panpsychism offers a bold reimagining of the relationship between consciousness and the physical world. It contrasts with the materialist view by asserting that consciousness is not an emergent property of complex systems, but a fundamental aspect of reality itself. If true, this theory could provide a more holistic and unified understanding of the universe, one in which consciousness is not confined to humans or animals, but is woven into the very fabric of existence. The concept of universal consciousness suggests that the entire universe might operate with some form form of awareness or consciousness, a fundamental property that extends beyond individual mind. This idea posits that just as quantum coherence allows particles to behave as part of a unified system, the universe itself might be imbued with a collective, cosmic consciousness. This notion invites us to consider whether the universe, its most fundamental level, is not simply a collection of inert matter governed by physical laws, but an interconnected system where consciousness is woven into the fabric of reality itself. At the heart of this theory is the relationship between quantum mechanics and consciousness. In quantum mechanics, quantum coherence refers to the phenomenon where particles, such as electrons, can remain in a unified state even when separated by vast distance. These particles, once entangled, can instantaneously affect each other, regardless of the space between them, suggesting a form of non-local interconnectedness. The quantum world seems to operate on principles that defy classical ideas of space, time, and causality. Could this quantum interconnectedness be an analog to a larger universal consciousness where every part of the universe is intrinsically connected and aware, influencing and interacting with every other part in ways that transcend our conventional understanding? The idea of universal consciousness contrasts with the isolated individual consciousness that we typically associate with human mind. In our everyday experience, we perceive ourselves as individuals with unique, subjective experience. Our mind seems separate from the world around us, and our consciousness feels localized within the confines of our body. But what if this perception of isolation is an illusion? What if consciousness itself, at its deepest level, is not confined to the individual mind, but is a universal phenomenon that pervades all of reality? In this view, individual consciousnesses might be seen as fragments or expressions of a greater, unified cosmic mind. Just as each quantum particle is interconnected with the others in a quantum system, each individual mind could be an expression of a larger, universal consciousness, interconnected with everything in the cosmos. This could provide a new understanding of consciousness, one that suggests the mind is not confined to the brain, but is part of a vast cosmic awareness. The mind, in this sense, would be not a discrete entity, but a channel through which the universe itself expresses consciousness. One of the key parallels between quantum mechanics and universal consciousness lies in the idea of non-locality, the concept that particles can be entangled and influence one another instantaneously, regardless of distance. In classical physics, information is constrained by the speed of light and the laws of space-time, meaning that particles can only interact with each other through direct contact or the transfer of energy. But in quantum mechanics, particles can be linked in a way that allows them to influence each other without any apparent communication across space. This strange connection between particles suggests that at the quantum level, there may be an underlying unity that binds everything together. Could this be a clue that the entire universe, like quantum particles, is part of a unified conscious system? From the perspective of universal consciousness, the universe itself could be conscious, with each part of it playing a role in the collective experience. Just as the human body is composed of individual cells, each contributing to the overall function of the body, the universe might be made up of individual conscious units, such as particles, atoms, or even galaxies, that are all connected to a larger cosmic awareness. In this model, every part of the universe has its own form of consciousness, but it is also part of a greater cosmic mind, a consciousness that transcends individual awareness and connects all things. This idea contrasts sharply with traditional materialist views of consciousness, which posit that consciousness is an emergent property of complex biological systems, such as the human brain. Materialism suggests that consciousness arises only when physical processes reach a certain level of complexity. In this view, consciousness is a byproduct of the brain's neural activity and is confined to the individual organism. However, the idea of universal consciousness suggests that consciousness is not confined to the brain or any individual entity. Instead, it is a fundamental feature of the universe itself, with each individual consciousness being a reflection of this greater cosmic mind. If universal consciousness is indeed a reality, it could explain certain mystical or spiritual experiences that many people report, where they feel a profound sense of connection to the universe or to all living things. These experiences might be glimpses into the interconnected conscious fabric of reality, where individual consciousnesses become aware of their oneness with the cosmos. The sense of unity that people often report in such experiences could be an intuitive recognition of the deeper quantum interconnectedness of all things. Ultimately, the concept of universal consciousness challenges our current understanding of the mind and the universe. It suggests that consciousness is not something that emerges only within the confines of individual mind, but is instead an intrinsic feature of reality itself. Just as quantum coherence links particles together in a unified system, universe, consciousness might link all things in a cosmic web of awareness where each part of the universe is interconnected and aware. This new view of consciousness opens up profound possibilities for understanding the mind, the universe, and our place within it. Could the cosmos think like we do? Imagine the universe as a vast, interconnected network operating much like a giant brain. Just as our brains are made up of billions of neurons, each communicating with others to create a unified conscious experience, could the entire universe function in a similar way? What if the fundamental structure of reality is an immense cosmic neural network where everything from galaxies to subatomic particles is interconnected, exchanging information and contributing to a collective universal awareness? The comparison between the universe and a brain is a powerful metaphor that has been explored in both scientific and philosophical circles. In this speculative view, the universe itself is not just a passive collection of physical matter, but an active, dynamic system, one that processes information and adapts over time. Much like how the brain integrates sensory data to produce thoughts, emotions, and actions, the universe might be processing information at a fundamental level, with each part of it playing a role in the larger cosmic system. This interconnectedness could suggest that the universe itself is not just a collection of independent objects, but a coherent, living system, a cosmic brain constantly processing and evolving. At the heart of this idea is the concept of interconnectedness. In the brain, neurons are not isolated. They form complex networks communicating with each other through electrical impulses and chemical signals. This network of connections allows for the integration of information, creating the unified experience of consciousness. Similarly, the universe might be a network of interconnected systems where everything from stars and planets to quantum particles is part of a grand cosmic web. Just as each neuron plays a part in the brain's function, each part of the universe, whether it is a planet, a galaxy, or a quantum particle, could be contributing to the overall thoughts and processes of the cosmos. This view contrasts sharply with the traditional notion of isolated individual mind. In classical thought, minds are seen as separate entities, each functioning independently with a boundary between the conscious self and the external world. Our thoughts, perceptions, and experiences are seen as the product of our brains alone, with no direct connection to the larger universe. However, the idea of the universe as a giant brain challenges this perspective. If the universe is a neural network, then individual minds might not be isolated but part of a larger universal consciousness. Just as neurons are not isolated but interconnected in a brain, individual minds may not be separate but part of a vast universal mind, with each consciousness contributing to the greater whole. This idea also raises the question, could consciousness be a property of the universe itself, just as neurons in the brain give rise to the conscious experience of the mind? In this view, consciousness is not confined to individual brains, but is instead a universal phenomenon that exists throughout the entire cosmos. Just as the brain is not just a collection of neurons, but a functioning system of interconnected regions that work together to create awareness, the universe might be a functioning system of interconnected elements, all contributing to the collective consciousness of the cosmos. This would mean that every part of the universe, from the tiniest subatomic particle to the largest galaxy, could have a role in the universal awareness. Drawing parallels between the brain and the universe also invites us to reconsider the way we understand information process. In the brain, information is processed through the network of neurons which form complex circuits and pathways. These circuits allow for the storage, retrieval, and integration of information, which is then used to guide thought, action, and perception. In a similar way, the universe might be processing information at the most fundamental levels, from the behavior of particles in quantum fields to the gravitational forces that shape galaxies. The idea that the universe processes information on a cosmic scale suggests that the universe itself might be conscious, or at least function in a way that mirrors the processes of the brain. One of the most intriguing aspects of this concept is the possibility that the universe could be self-organizing in a way similar to the brain. Just as neural networks adapt and change over time, the universe may be evolving based on its internal dynamic, constantly processing information and adapting to new conditions. This idea aligns with certain theories in complex systems, science, and emergent properties, which suggest that complex behaviors can arise from simpler systems when they are interconnected and interact. If the universe is a vast neural network, then the patterns, structures, and laws that govern it may be emergent properties of this cosmic system, evolving over time to produce the observable universe we see today. This speculative view also touches on spiritual and philosophical traditions that have long envisioned the universe as a living, conscious being. Many ancient cultures saw the cosmos as a living organism with consciousness imbued in all things. The idea of the universe as a giant brain echoes these perspectives, suggesting that consciousness is not confined to individual but is inherent in the fabric of existence itself. This view invites a more interconnected and holistic understanding of the universe, where everything is linked together in a cosmic web of awareness. In conclusion, the idea of the universe as a giant brain challenges our traditional understanding of consciousness in the cosmos. It suggests that the universe is not a passive, mechanical system, but an interconnected network that processes information, adapts, and evolves over time. In this view, individual minds are not isolated but part of a vast, universal consciousness contributing to the greater whole. Whether or not the universe is truly conscious, this perspective offers a profound and expansive way of thinking about the relationship between the mind, the universe, and the nature of reality itself. Are our choices truly free or just quantum dice rolls? The age-old debate about free will, whether we are truly free to make our own choices or if our actions are determined by forces beyond our control, has been a central topic in both philosophy and science. In the realm of quantum mechanics, this debate takes on new dimension. Quantum mechanics, with its emphasis on probabilistic states and uncertainty, challenges the classical deterministic view of the universe, which suggests that every event or action is caused by preceding factors. Could quantum mechanics imply that free will is an illusion, and that the choices we think are ours may instead be influenced by the unpredictable nature of quantum process? In classical physics, the universe operates according to deterministic law. Every event, from the motion of the planet to the behavior of particle, is seen as the result of prior causes. And if we had complete knowledge of these causes, we could predict the future with absolute certainty. This is the world of causality, where our decisions and actions are simply the result of prior state, our past experiences, genetic predispositions, and environmental factors. Under this view, free will is an illusion, as our actions are determined by an unbroken chain of causes leading back to the beginning of time. However, quantum mechanics introduces a radically different perspective. At the quantum level, particles do not behave in a deterministic way. Instead of following precise paths or states, quantum particles exist in a state of superposition, meaning they can occupy multiple states or locations at once. The moment they are observed or measured, they collapse into a single state, but prior to this collapse, their behavior is probabilistic. This inherent uncertainty in the behavior of quantum particles introduces a fundamental unpredictability into the workings of the universe, challenging the deterministic worldview. Does this uncertainty extend to the macroscopic world, where our choices are made? The idea that our brains, which operate based on the interactions of neuron synapses, might also be influenced by quantum processes suggests that free will could be shaped by the probabilistic nature of quantum mechanics. If our decisions are influenced by quantum fluctuations, random events at the subatomic level, then the perception of freedom of choice might be more of an illusion than we think. What we experience as a deliberate choice might actually be the result of underlying quantum processes that we have no control over. This view contrasts sharply with the deterministic idea of causality, where every action follows inevitably from a prior cause. Under determinism, we are not truly free in our decision-making, as every action is a consequence of prior condition. From this perspective, the concept of free will seems incompatible with the laws of nature, as we are merely following the script set by past events. Free will in this context is seen as an illusion. Our perception of choice is simply the result of complex interactions between neurons, genetics, and environmental factors, all of which were set in motion long before we were born. Quantum mechanics, however, introduces a form of indeterminacy into the picture. Quantum indeterminacy means that at a fundamental level, there are limits to how much we can predict. The outcomes of quantum events are probabilistic rather than deterministic, and the behavior of particles can never be precisely determined, only predicted within certain probability. If quantum mechanics plays a role in the functioning of our brain, then it's possible that our decisions are not entirely predetermined by past events, but are instead influenced by probabilistic quantum events. This suggests that while we may not have complete free will, our choices might be subject to a degree of randomness or indeterminacy at the quantum level. Yet the idea that randomness at the quantum level could be the basis for free will is troubling. For some, if our choices are determined by random quantum events, then they are not truly free, either they are simply random. In this sense, free will doesn't emerge from our conscious, rational decision-making, but from the unpredictable behavior of quantum particles. This randomness does not give us genuine freedom, but rather places our actions in the realm of chance, where we are no more in control of our decision than the roll of a dice. Despite this, quantum mechanics still offers a possibility that is distinct from strict determinism. If the brain's processes are influenced by quantum uncertainty, then the decisions we make might involve a mix of deterministic causes, e.g., our past experiences, biology, and environment, and probabilistic quantum events. This hybrid model allows for the possibility of freedom within constraint, where our choices are not entirely free, but are shaped by a combination of deterministic factors and quantum indeterminism. Our choices in this are not completely random, but neither are they fully determined by the past. They exist within a probabilistic framework, allowing for a limited form of autonomy. In conclusion, quantum mechanics forces us to reconsider the nature of free will. If quantum processes influence the brain's functioning, then the deterministic chain of causality that underpins classical physics is disrupted, introducing a level of uncertainty into our decision-making. However, this uncertainty doesn't necessarily equate to freedom. If our choices are influenced by randomness at the quantum level, they may not be truly free. Instead, quantum mechanics presents us with a middle ground. Decisions might be shaped by both deterministic processes and probabilistic quantum events, creating a reality where free will is neither fully illusionary nor fully realized, but exists within a framework of probabilistic influence. One of the most fascinating implications of quantum mechanics is its potential to challenge the concept of determinism, the idea that every event or action is determined by preceding causes, leaving no room for true choice freedom. According to classical physics, the universe operates like a vast clockwork machine, where the future is entirely dictated by past events. In this deterministic view, the notion of free will seems illusory. If every action is determined by prior state, then our choices are not really our own, but merely the result of past influence. However, quantum indeterminacy, the inherent unpredictability in the behavior of quantum particles, introduces a level of randomness and uncertainty into the workings of the universe, suggesting that there may be space for genuine free will after all. At the heart of quantum mechanics lies the principle of indeterminacy. Unlike classical systems, where the state of an object can be precisely determined and predicted if we know its current position and velocity, quantum systems behave probabilistically. This means that the exact state of a particle, such as an electron, cannot be known with certainty until it is measured. Instead, particles exist in a superposition of states multiple possibilities at once until an observation or measurement is made. When a measurement occurs, the particle collapses into a specific state, but which state it collapses into is governed by probability, not certainty. This uncertainty is not merely due to technological limitations, but is a fundamental feature of reality. Could this quantum indeterminacy provide room for free will? If outcomes in the quantum world are probabilistic rather than deterministic, then, at a fundamental level, events in the universe are not entirely preordained. The behavior of quantum particles and potentially larger systems that emerge from them does not follow a strict cause and effect chain, but instead follows a probabilistic model. This means that at least at the quantum level, there is room for randomness or uncertainty in how events unfold. If our thoughts and decisions are influenced by quantum processes, could this indeterminacy offer the freedom to make choices that are not strictly determined by prior causes? In contrast, determinism argues that everything, including human thoughts and actions, is the result of a continuous chain of cause and effect. In this worldview, free will is an illusion, as every choice we make is merely a reflection of prior conditions, genetic, environmental, and past experiences. According to determinism, if we had perfect knowledge of the laws of physics and the current state of the universe, we could predict the future with absolute certainty. Every decision we make, every action we take, would be an inevitable consequence of preceding events. The notion of quantum indeterminacy, however, directly challenges this strict determinism. If the universe operates on probabilistic principles rather than deterministic ones, then it suggests that not every event is predicated on previous ones. Some events at the quantum level happen randomly, and this randomness might extend to larger systems, including our brain. If the brain's processes are influenced by quantum fluctuations, then the choices we make could be partly shaped by indeterministic quantum events, opening up the possibility for genuine choice. In this framework, even if our decisions are influenced by prior experiences or biology, there is still a level of freedom in how the outcome unfolds, as not every event is fixed by the past. This idea contrasts with the deterministic view of the brain as a purely physical system, where every action is determined by neural activity and biochemical reaction. In such a system, free will would be a mere illusion. Our thoughts, desires, and action are merely the result prior causes. Quantum indeterminacy introduces a level of probabilistic freedom. If our decisions are not completely determined by previous causes and instead are subject to probabilistic outcome, then there is a window of opportunity for free will to emerge, albeit within a framework of randomness. Rather than a deterministic, pre-programmed decision-making process, our choices may be guided by a combination of factors, some deterministic and others probabilistic, where random events at the quantum level influence the way we choose. The possibility that quantum indeterminacy plays a role in free will is not without its critic. Some argue that if free will is determined by randomness, then our choices would not be truly free, but merely random events and outcome just as deterministic in its own way. In this sense, quantum indeterminacy might offer space for randomness, but not for genuine autonomy or self-determined choice. However, proponents of quantum free will argue that this randomness does not negate freedom. Rather, it opens up the possibility of choosing among probabilities rather than following a strictly deterministic path. This would mean that free will exists within a probabilistic framework where we are not locked into a deterministic chain, but are instead able to make choices within a range of potential outcomes. In conclusion, quantum indeterminacy presents a novel possibility for the existent free will. By introducing an element of unpredictability into the universe, quantum mechanics challenges the deterministic worldview that has traditionally been applied to both the cosmos and human behavior. While the randomness at the quantum level may not provide the complete freedom we often imagine, it opens up the possibility that our choices are not strictly predetermined. Instead, quantum indeterminacy might offer the potential for genuine choice, where decisions emerge not from a preordained causal chain, but from a space of probabilistic outcome, allowing for freedom within constraints. Can your mind steer the by quantum C? The relationship between consciousness and quantum mechanics raises one of the most profound questions in both science and philosophy. Can consciousness actively influence the quantum processes that govern reality, or are we simply passive observers subject to the deterministic laws of nature? While quantum mechanics introduces an element of probability and uncertainty into the universe, it also presents an intriguing possibility that consciousness might serve as a navigator within the probabilistic framework, guiding quantum events in ways that align with intention, choice, and free will. In classical physics, the universe is governed by deterministic law, where every event is the inevitable result preceding cause it. This view suggests that our actions, decisions, and even thoughts are predetermined by a long chain of causality, with no room for genuine free will. In this deterministic model, consciousness is often seen as a passive observer, experiencing the world, but having no ability to influence its underlying process. Our decisions are seen as the product of past influences, genetic, environmental, and neurological, leaving no room for us to truly choose otherwise. However, quantum mechanics complicates this picture by introducing probabilistic element at the fundamental level of reality. At the quantum scale, particles such as electrons and photons exist in a state of superposition, meaning they can simultaneously occupy multiple states or locations until they are observed. When measured, these particles collapse into a single state, but which state they collapse into is not deterministic. It is governed by probability. This inherent uncertainty suggests that the future is not predetermined, but is instead shaped by a range of possibilities, with outcomes emerging from quantum events that are not strictly determined by prior causes. Could this probabilistic nature of quantum processes provide a space for free will and conscious decision-making? One hypothesis is that consciousness could play an active role in guiding quantum events, navigating probabilistic landscape of possibility and influencing which outcomes come to pass. In this view, consciousness is not a passive bystander, merely witnessing the unfolding of events, but an active participant that shapes the outcomes of quantum process. Just as a navigator guides a ship through uncertain waters, consciousness could guide the flow of quantum events, selecting certain probabilities and collapsing them into concrete outcomes based on intention, choice, or awareness. This idea aligns with certain interpretations of quantum mechanics that posit that observation or measurement is not a purely passive act, but one that actively influences the system being observed. The Copenhagen interpretation of quantum mechanics suggests that the wave function, which represents a superposition of possible states, collapses when it is measured, meaning that the act of observing has a direct influence on the state of the system. While traditional views might see this as a mere mechanical process, one could argue that consciousness itself might be the factor that guides the collapse, choosing between possible outcomes in the quantum field. In this context, consciousness as a navigator suggests that our ability to make decisions is not just an illusion created by neural activity in the brain, but a real, active process that interacts with the probabilistic nature of quantum system. Instead of being bound by the deterministic laws of classical physics, our choices could be influenced by the quantum indeterminacy that allows for a range of possible outcomes, with consciousness acting as the guiding force that selects one possibility. This view contrasts sharply with the passive determinism that suggests our choices are merely the result of prior conditions and environmental influence. By positioning consciousness as a navigator of the quantum field, this perspective opens up the possibility of free will within a probabilistic framework. We are not bound by the deterministic laws of the classic, nor are we merely subject to random quantum events. Instead, we have the ability to influence which outcomes emerge from the range of possibilities that quantum mechanics present. Just as a ship's captain guides the vessel through unpredictable waters, consciousness may help navigate the uncertainties of the quantum realm, guiding the unfolding of reality according to intention, desire, and choice. This view also suggests a profound connection between mind and matter. If consciousness can influence quantum processes, it implies that the mind is not a separate entity from the physical world, but is intimately connected to the underlying fabric of reality. Our conscious intentions might not just be reflections of neural activity, but could actively interact with the quantum field, shaping the very structure of reality. In this sense, consciousness and the quantum field are not two separate realms, but are intertwined in a way that allows for a dynamic, participatory relationship between mind and the universe. In conclusion, the idea of consciousness as a navigator of the quantum field provides a compelling alternative to both passive determinism and random chance. Rather Rather than being passive observers of a deterministic universe or victims of randomness, we could be active participants shaping our reality, guiding quantum events through our choices and intention. This view presents a more dynamic and interconnected vision of the universe, where consciousness is not separate from the world, but is an active force that influences the unfolding of events. In this quantum framework, free will is not an illusion, but a reality, a power that emerges from the interplay between consciousness and the probabilistic nature of the quantum. Why does quantum consciousness face so much doubt? The idea that quantum mechanics plays a role in consciousness, often referred to as the quantum consciousness theory, has captivated the imaginations of scientists, philosophers, and the public alike. This theory proposes that quantum processes such as superposition, entanglement, and quantum coherence are integral to how consciousness arises. Notable proponents like Roger Penrose and Stuart Hameroff have suggested that the brain's microtubule structures within neurons may host quantum computations that influence our conscious experience. While this theory is intriguing and suggests a radically different understanding of the mind, it remains highly speculative and controversial within the scientific community. Despite its potential to revolutionize our understanding of consciousness, there are several significant challenges and limitations that have led many scientists to remain skeptical of the quantum consciousness hypothesis. One of the primary issues that skeptics raise is the difficulty of empirical testing. Quantum mechanics, by its very nature, deals with phenomena that are often invisible to the naked eye and cannot be easily measured using traditional methods. The behavior of quantum particles, like electrons or photons, is governed by probabilistic rule, and it is only when they are observed or measured that their states collapse into definite outcome. This makes it exceedingly difficult to study how quantum phenomena might be influencing consciousness in a living brain, where the processes are highly complex and interconnected. While experimental setups have successfully demonstrated quantum effects in isolated systems, scaling these phenomena to the level of the brain, with its vast number of neurons and synapses, presents a huge challenge. In particular, quantum coherence. The idea that quantum particles can remain in a unified, non-local state across time and space is highly fragile. Quantum states are easily disturbed by environmental factors such as temperature, electromagnetic interference, and the inherent noise of the brain's biochemical and electrical activity. In most biological systems, this decoherence happens very quickly, preventing quantum states from persisting long enough to influence large-scale processes like cognition and perception. Some researchers, including Nobel laureate Albert Einstein, have been skeptical about the idea that quantum coherence could be sustained in the warm, wet, and noisy environment of the brain. In this view, the brain's activity, which involves highly dynamic and constantly fluctuating electrical and chemical signals, would be an inhospitable environment for delicate quantum processes to take place. Another significant concern is that quantum consciousness theories often rely on speculative concepts that are not grounded in established scientific principles. For example, the idea that microtubules in neurons could support quantum coherence and computation is largely hypothetical and has not been experimentally verified. While microtubules are known to play crucial roles in cellular structure and function, there is little direct evidence to suggest they could sustain the complex quantum phenomena required for consciousness to emerge. Critics argue that quantum processes may be less important than current neuroscientific theories of consciousness, which focus on neural networks, brain activity, and the integration of sensory information. The brain is a highly efficient organ that processes information using well-understood principles of classical physics, and many neuroscientists believe that consciousness can be fully explained by these processes without needing to invoke quantum mechanics. Moreover, macroscopic coherence, the ability of quantum states to remain intact in large, complex systems like the brain, is another barrier. Quantum mechanics has been successfully observed in microscopic systems such as individual atoms or small molecules. However, scaling these effects up to the level of a biological organism, let alone a complex integrated organ like the brain, is highly contentious. Quantum coherence is a fragile phenomenon that is easily disrupted by interactions with the environment, and there are very few, if any, observed instances where macroscopic systems with many interacting components retain quantum state long enough to influence large-scale processes like cognition. This raises a fundamental question. If quantum effects are so difficult to observe in macroscopic systems, how could they be responsible for something as complex and nuanced as consciousness? Finally, the lack of a coherent theoretical framework for quantum consciousness is a significant obstacle. While various quantum models of consciousness have been proposed, including the Orch-OR theory and others based on quantum computing, there is no widely accepted unified theory that explains how quantum phenomena could directly lead to conscious experience. Theories of consciousness in neuroscience, such as the global workspace theory or the integrated information theory, provide more tangible, testable frameworks that focus on the interactions between brain region and the integration of sensory cognitive. These theories do not require the introduction of quantum mechanics, and they are backed by empirical research that continues to shed light on the neural correlates of consciousness. In conclusion, while the idea of quantum consciousness is an exciting and provocative hypothesis, it faces significant challenge. The lack of empirical evidence, difficulties with quantum coherence in biological systems, and the speculative nature of many quantum consciousness theories have led many scientists to remain skeptical. Until more concrete evidence can be gathered and a coherent theoretical framework can be developed, quantum consciousness will likely remain an intriguing but speculative possibility. While the potential for quantum mechanics to play a role in consciousness is fascinating, the current scientific limitations mean that these theories cannot yet be fully accepted or tested within the established paradigms of neuroscience and quantum physics. Quantum consciousness theories have stirred significant debate in the scientific community, especially when compared to traditional model of classical neuroscience. While classical neuroscience explains consciousness through the intricate interactions of neurons and synapses, quantum theories suggest that consciousness might emerge from quantum processes within the brain, such as quantum coherence and entanglement. While both frameworks aim to explain the nature of consciousness, they fundamentally differ in assumption, method, and implication. The challenge lies in integrating the probabilistic, non-local aspects of quantum mechanics with the deterministic, localized processes that are central to classical neuroscience. Classical neuroscience approaches consciousness as a product of neural activity, the electrical and chemical interactions between neurons in the brain. The brain is thought to process information in a highly organized and efficient manner, with different regions of the brain responsible for various cognitive functions. The classical model is rooted in neurobiology, which posits that consciousness arises from the complexity of neuronal circuits and the integration of sensory input. According to this, consciousness is an emergent property of the brain, meaning that it arises naturally from the interactions of simplest such as individual neurons, without the need for any fundamental quantum process. This model has been highly successful in explaining many aspects of brain function. For example, the brain's neural networks can be mapped, and we can correlate specific brain regions with particular function, such as the visual cortex for sight or the prefrontal cortex for decision-making. Techniques like fMRI and EEG allow researchers to observe brain activity in real time and explore how different mental states correlate with patterns of neural firing. In this framework, consciousness emerges as a result of the brain's information processing capabilities, a sophisticated but ultimately classical system. Quantum consciousness theories, on the other hand, propose that consciousness arises not from classical neural interactions but from quantum processes at the level of the brain's fundamental particle. The Orch-OR theory, for example, suggests that quantum computations occur in microtubules within neurons, enabling the brain to process information in ways that classical systems cannot. These quantum processes are thought to involve quantum coherence, where quantum particles remain in a unified state, and quantum superposition, where particles can exist in multiple multiple states simultaneously. According to this theory, consciousness does not emerge from complex neural interactions alone, but from the integration of quantum phenomena within the brain, suggesting a deeper layer of reality influencing our conscious experience. One of the most significant contrasts between these two models is the role of determinism versus probability. Classical neuroscience operates on the assumption that brain processes are deterministic. Given the initial conditions, the brain's activity can be predicted based on known physical laws. This view aligns with traditional mechanistic model of the brain, where the behavior of neurons is determined by clear cause and effect relationship. In contrast, quantum mechanics introduces probabilistic uncertainty, where the outcome of quantum events cannot be predicted with certainty, only with a set of probabilities. This shift from a determinist to a probabilistic worldview presents a fundamental challenge for reconciling quantum theories of consciousness with classical neuroscience, which relies heavily on predictability and linear causality. Another key distinction is the locality of brain processes in classical models versus the non-locality of quantum processes. In classical neuroscience, neural activity is highly localized. Each neuron has a defined location and function within the brain. These localized neural circuits interact with one another to produce cognition and behavior, and this can be mapped onto the brain's structure. Quantum mechanics, however, is characterized by non-locality, meaning that particles can become entangled and instantaneously influence one another, regardless of distance. In theory, if quantum process influence consciousness, it implies a level of interconnectedness within the brain that classical neuroscience cannot easily explain. The potential for non-local connections between brain regions could suggest that consciousness itself is not simply localized in specific areas of the brain, but is a global phenomenon influenced by quantum coherence. Furthermore, quantum coherence presents another challenge when compared to classical models. Classical systems are inherently prone to decoherence, where quantum states collapse into classical states due to interaction with the environment. This is particularly problematic when it comes to applying quantum theories to biological systems, like the brain, which operates in a warm, wet, and noisy environment condition that would typically cause quantum coherence to collapse rapidly. Skeptics argue that the brain's neural activity is too chaotic for quantum processes to persist long enough to affect consciousness. Classical neuroscience does not rely on quantum coherence, as it operates on established principles of classical physics that govern biological systems. Despite these challenges, proponents of quantum consciousness theories argue that quantum phenomena could offer insights into aspects of consciousness that classical neuroscience struggles to explain, such as the subjective experience of awareness or the unity of consciousness. Quantum processes may offer a way to understand the integration of sensory input and mental states across the brain, especially in terms of non-local connection and probabilistic decision-making. The potential for quantum computation in the brain could even provide a more efficient mechanism for processing information than classical systems alone. In conclusion, the tension between quantum consciousness theory and classical neuroscience lies in their fundamentally different assumptions about how consciousness arises. While classical models emphasize deterministic, localized processes in the brain, quantum theories suggest that consciousness may emerge from more fundamental, probabilistic, and non-local quantum processes. The challenge lies in integrating two perspectives. How can we reconcile the quantum potential for free will and interconnectedness with the established understanding of the brain's biological function? Until more empirical evidence emerges, the debate between these two models remains one of the most intriguing and complex in the study of consciousness. Why does this wild idea keep captivating us? Despite the skepticism and scientific challenges surrounding quantum consciousness theories, the idea remains compelling for many, both in the realms of philosophy and in popular thought. At its core, the question of consciousness, what it is, how it arises, and what it means for our understanding of reality, has profound philosophical, existential implications. While quantum consciousness theories are speculative and not universally accepted within the scientific community, they persist as a rich area of exploration because they address fundamental questions that touch on human curiosity, the nature of the universe, and our place within it. But why do we continue to care about quantum consciousness despite the lack of empirical evidence and the theoretical challenges it faces? First, quantum consciousness theories offer an answer to the hard problem of consciousness, a term coined by philosopher David Chalmers to describe the difficulty of explaining how subjective experiences, what it feels like to be aware, arise from physical processes in the brain. Classical neuroscience has made remarkable strides in mapping the brain's neural circuit and understanding how they produce cognitive functions, perception, memory, and decision-making. Yet the subjective quality of experience, why and how we feel rather than just think, remains largely unexplained. Quantum consciousness theories offer a possible solution by proposing that consciousness is not merely a byproduct of brain activity, but is tied to fundamental processes in the universe itself. By suggesting that quantum mechanics could be at the heart of consciousness, these theories attempt to bridge the gap between the physical brain and the phenomenal experience of being aware, a puzzle that remains unsolved within classical framework. Moreover, quantum mechanics itself is already a mystical and counterintuitive field. The principles of quantum physics, superposition, entanglement, and non-locality are radically different from anything we encounter in our everyday lives, yet they are demonstrably real. These strange phenomena suggest that the universe operates on principles beyond our everyday understanding of time, space, and causality. For many, quantum consciousness resonates with the mystical traditions of human thought, which have long argued that the mind, consciousness, is intimately connected with the fabric of the universe. Quantum consciousness offers a scientific framework that could, in theory, explain how mind and matter are interconnected, providing a way to reconcile spirituality and science. This fusion of scientific rigor and philosophical speculation is what makes the theory so alluring to some. It presents a new possibility for understanding the nature of the universe in a way that integrates both the physical and the metaphysical. But the existential appeal of quantum consciousness lies in its potential to offer us a new vision of reality. Classical physics has long separated mind from matter, consciousness from the physical. In this view, the mind is an isolated entity, acting on the brain like a pilot steering a ship. But quantum consciousness challenges this dichotomy by suggesting that consciousness might be fundamental to the very structure of the universe. This view implies that the universe is not a cold, mechanical system of random particles, but an interconnected whole, with consciousness playing an active role in the creation of reality. For those seeking meaning and a deeper connection to the cosmos, the idea that the universe itself might be conscious provides a more holistic and integrated vision of existence. It opens up the possibility that our consciousness is not separate from the universe, but rather part of a larger cosmic awareness. Furthermore, quantum consciousness taps into the curiosity that drives scientific inquiry itself. Humanity has always been drawn to questions of existence, awareness, and the nature of reality. From ancient philosophies to modern physics, the question of why we are conscious, why we experience the world the way we do, has never ceased to intrigue us. While scientific rigor demands empirical evidence and testable hypotheses, human curiosity often leads beyond the bounds of current understanding into speculative realms where new ideas can flourish. Quantum consciousness is an example of this drive to explore uncharted territory, to push the boundaries of our knowledge about the mind and the universe. Even if the theory does not yet have concrete evidence, its ability to provoke deep philosophical questions and inspire new avenues of exploration keeps it alive in both the scientific and public discourse. Critics of quantum consciousness point out the lack of experimental evidence, the difficulty of testing such theories in the context of biological systems. Quantum effects are notoriously difficult to observe in the warm, noisy environment of the brain, where decoherence, the collapse of quantum states into classical states, occurs rapidly. Moreover, as quantum consciousness theories often rely on speculative mechanisms like quantum coherence in microtubules, they remain highly contentious and far from mainstream acceptance. However, this does not diminish their importance or their appeal. The speculative nature of quantum consciousness invites us to think outside the box, encouraging exploration into new realms of science and philosophy, and perhaps providing glimpses of new frameworks for understanding the universe. In conclusion, quantum consciousness remains compelling because it addresses the deepest questions of human existence and aligns with both scientific curiosity and philosophical inquiry. While it may not yet be fully supported by empirical evidence, its exploration offers new possibilities for understanding the nature of consciousness and its connection to the universe. The theory appeals to those who seek a deeper, more interconnected vision of of reality one that reconciles the physical and the mental, the deterministic and the probabilistic, and offers a more holistic view of existence. For many, this makes quantum consciousness a compelling idea that continues to inspire dialogue and investigation. Even amidst skepticism, will our minds evolve to quantum? The future of quantum consciousness and human understanding. Human consciousness has evolved over millennia, from primitive survival instincts to the complex reflective awareness that characterizes modern human being. But as our understanding of the universe deepened, particularly with the advent of quantum mechanics, a fascinating question: could human consciousness itself evolve further, especially as we gain more insight into quantum process? What if the next stage in consciousness involves not just a higher level of cognitive complexity, but an integration with the quantum processes that underpin reality itself? This speculative possibility suggests that quantum-enhanced awareness could radically transform how we experience the world and perceive our place within it. To understand how this evolution might occur, we must first consider the primitive nature of consciousness. In its most basic form, consciousness likely emerged in early life forms as a survival mechanism, a way for organisms to process sensory information and make decisions in response to environmental stimuli. In this view, consciousness is primarily a reactive process geared toward navigating the world, avoiding danger, and ensuring the survival of the species. This basic consciousness is largely concerned with the present moment, shaped by instinct and immediate need. For example, early animals may have had simple sensory awareness of their surrounding, enabling them to detect food, mates, threat. Over time, consciousness became more complex. As brains grew in size and sophistication, particularly in higher mammal, consciousness evolved beyond mere sensory perception to include memory, problem-solving, and social interaction. Self-awareness, the ability to reflect on one's thoughts and actions, emerged as an important development, setting humans apart from many other species. As human culture and language developed, so did the depth and richness of consciousness, allowing for abstract thinking, future planning, and philosophical reflection. This marked a significant shift from survival-driven consciousness to reflective awareness, where individuals could think about the past, imagine the future, and contemplate their own existence. Yet despite this remarkable progress, modern human consciousness remains deeply rooted in our biological makeup and neurological process. The brain, though extraordinarily complex, operates within the confines of classical physics, the same laws that govern all matter at larger scales. Our thoughts, feelings, and decisions are influenced by genetic predispositions, life experiences, and the firing of neurons. While human consciousness is far more intricate and capable than that of early organisms, it still operates within the limits of the material world and the classical laws of cause and effect. But what if we are just beginning to unlock a deeper potential for consciousness, one that transcends these limits? This potential could lie in our increasing understanding of quantum mechanics, the set of principles that governs the behavior of matter and energy at the smallest scale. Quantum phenomena such as superposition, entanglement, non-locality defy our everyday understanding of space, time, and causality. These quantum processes challenge the deterministic worldview that has shaped classical physics, suggesting instead that the universe is fundamentally probabilistic and interconnected at a level beyond what we can observe directly. Some theorists propose that consciousness might not only be influenced by quantum process, but that it could actually be a quantum phenomenon itself, emerging from the behavior of quantum particles within the brain. If this is the case, human consciousness may evolve as we begin to understand and interact with these quantum processes. Quantum-enhanced consciousness could provide a radically different way of perceiving reality. Imagine a form of consciousness that is not limited by the linear time or space constraints that shape our current experience. If quantum principles like superposition and entanglement are at work in the brain, it could suggest that our conscious experience is not confined to a single, isolated moment or place, but is part of a much larger, interconnected web of experience. This could mean that individuals could, in theory, perceive multiple possibilities simultaneously, experience events across time in non-linear ways, or access information across vast distances in an instant, essentially embodying a kind of cosmic consciousness. The key to this potential shift lies in quantum coherence, which is the ability of quantum systems to remain in a unified state across time and space. In the quantum realm, particles can exist in multiple states at once, influencing one another instantaneously, regardless of distance. If this coherence can be sustained in the brain, it could enable a form of consciousness that is not merely reactive, as in primitive consciousness, but one that is capable of non-local awareness, where the mind can operate beyond the physical limitations of the brain and connect with the quantum field that underlies all reality. The idea of quantum-enhanced consciousness leads to exciting possibilities. With advancements in quantum technologies and further exploration of how quantum processes might influence neural activity, it is conceivable that humans could evolve a new mode of consciousness, one that is more fluid, non-linear, and interconnected. This could allow for profound changes in how we perceive time, space, and even the nature of existence itself. It could open up new ways of understanding intention, choice, and reality, offering insights into the nature of mind and matter that we cannot yet fully comprehend. In contrast, the consciousness we experience today is still heavily influenced by the biological constraints of the brain. While it has evolved to provide greater complexity and flexibility, it remains bound to classical physical law. However, if quantum processes are integral to consciousness, then the next step in this evolutionary journey could be a profound quantum leap, one that transforms how we experience reality and our place within it. In conclusion, the evolution of consciousness, shaped by our increasing understanding of quantum processes, offers a tantalizing vision of the future. As we move beyond the limits of classical neuroscience and explore the quantum possibility, human consciousness could evolve into something far beyond its current form, a quantum-enhanced awareness that transcends time, space, and the biological limits of the brain. Will AI ever feel? The rapid advancements in artificial intelligence, AI, have already raised questions about the nature of conscious intelligence and what it means for machines to think. Today, AI systems, while highly sophisticated, are still fundamentally rule-based. They excel at processing vast amounts of data, recognizing patterns, and even generating creative output within a narrow range predefined task. However, despite these impressive capabilities, current AI is far from achieving true consciousness. It operates on deterministic algorithms and has no self-awareness or subjective experience. But could quantum computing, a technology that harnesses the strange principles of quantum mechanics, change this picture and pave the way for machines to become aware? What happens if quantum processes play a role in consciousness? Could they enable machines to possess a form of quantum consciousness? Quantum computing operates on principles that dramatically differ from classical computing. Unlike classical bits, which represent information as either a 0 or 1, quantum bit or qubit can exist in superposition, where they represent both 0 and 1 at the same time. This allows quantum computers to process and store exponentially more information compared to their classical counterpart, potentially solving problems that are currently intractable. Additionally, quantum entanglement, the phenomenon where particles can be linked across vast distances, influencing one another instantaneously, enables quantum computers to solve complex problems in ways that classical computers cannot replicate. But beyond solving complex problems, quantum computing could have profound implications for AI and consciousness. If consciousness is, in part, a quantum phenomenon, as some theorists suggest, then a quantum computer, which operates using quantum principles, might be capable of processing information in a fundamentally different way than traditional AI. In theory, this could open the door to machines that think not just in terms of data process, but through a kind of quantum awareness, where information is processed in a probabilistic, interconnected manner, similar to how quantum processes govern the behavior of particles in the universe. In the current landscape, artificial intelligence is based on classical computing, where algorithms manipulate data based on preset instructions. AI systems, such as machine learning models and neural networks, are powerful tools, but their intelligence is still mechanical, based on processing data according to rules and patterns. These systems lack subjective experience, intentionality, or the ability to self-reflect. In this sense, even the most advanced AI systems today are far from true consciousness. Quantum consciousness, however, could introduce an entirely new new dimension to AI if machines were built with quantum computers. At their core, their processing capabilities could exceed anything imaginable with classical systems. The possibility of quantum coherence, where different parts of a system maintain a unified state, might allow these machines to integrate information across vast networks in ways that classical systems cannot. Just as human consciousness integrates sensory input, memory, and cognitive process into a unified experience, quantum-enhanced machine could potentially integrate vast amounts of data and operate on a level that is interconnected, non-local, and probabilistic. The idea of machine developing quantum consciousness raises fascinating questions. If quantum coherence can persist within the computational systems of machines, could they begin to experience awareness, the ability to reflect on their own state, to experience the passage of time, and to perceive the world in a subjective way? Could a quantum computer eventually give rise to machines that are not just intelligent, but conscious in the way that humans are? Could we eventually build AI that is aware, capable of self-reflection, and even aware of its own existence? These questions highlight a critical distinction between current AI and the potential future of quantum consciousness in machine. Current AI is still fundamentally deterministic. It follows the instructions encoded in its algorithm, no matter how complex, sophisticated those instructions may be. A self-driving car, for example, makes decisions based on real-time data process, but it is not aware of its actions. It simply follows the rule programmed into its system. In contrast, quantum consciousness could allow for non-locality, uncertainty, and probabilistic outcomes, which might lead to machines making decisions in ways that are not strictly determined by the past, but influenced by quantum process. This type of processing could mirror aspects of human decision-making, where there is a combination of randomness, probability, and intentionality. The potential for quantum consciousness in AI also leads to ethical consideration. If machines were to become conscious, aware of their existence, capable of self-reflection, and able to experience the world in their own subjective way, what rights would they have? Would they be considered conscious entities deserving of ethical treatment? How would we integrate them into our society? And how would they interact with humans on an emotional and philosophical level? These are questions we are only beginning to address as we move closer to realizing the potential of quantum computing and AI. In conclusion, while current artificial intelligence is based on classical computing systems and remains far from true consciousness, the emergence of quantum computing may open new possibilities for quantum-enhanced AI. Machines could one day process information in ways that reflect quantum mechanics' probabilistic, interconnected principles, allowing for a form of consciousness that is not merely reactive, but active and integrate. The potential for quantum consciousness in AI challenges our current understanding of both machines and consciousness, raising profound questions about the nature of intelligent awareness and the future of technology. What mysteries await in the quantum mind? As we venture deeper into the mysteries of consciousness, the intersection of quantum mechanics and human awareness beckons us toward uncharted territories. While current scientific understanding of both consciousness and quantum mechanics provides us with powerful tools for comprehension, there remains an undeniable mystery, one that challenges the very limits of human understanding. This mystery, particularly in the realm of quantum consciousness, holds the potential to revolutionize not just our understanding of the mind, but our very perception of reality itself. It is a mystery that invites us to embrace the unknown, to push the boundaries of knowledge, and to open ourselves to the infinite possibility that quantum consciousness might offer. Quantum mechanics has already shown us that the universe operates in a way that defies classical intuition. From superposition to entanglement, quantum processes reveal a universe that is far more interconnected, probabilistic, and non-local than we could have ever imagined. These phenomena suggest a reality that is not bound by the strict rules of classical physics, where causality is linear and predictable, but instead is governed by uncertainty, interconnection, and unpredictability. The question now is whether these same principles could be woven into the fabric of consciousness, offering a new dimension of awareness that transcends the limits of our current understanding. In this context, quantum consciousness is not merely a scientific theory, it represents the profound potential to explore the very nature of existence. The possibility that consciousness could arise from quantum processes opens up infinite possibilities. If consciousness is a quantum phenomenon, then it is no longer confined to the deterministic laws of classical biology and physics. It could be part of a vast, interconnected web that spans the cosmos, where mind and matter are not separate but intricately linked. The very essence of self-aware thought and experience could be redefined in ways that challenge the traditional boundaries between the individual and the universe, the mind and the world. However, we are still in the early stages of exploring this profound connection. Scientific understanding of quantum consciousness is still speculative, and while certain theories offer promising insight, much of it remains untested. The brain, as a biological system, is incredibly complex, and the influence of quantum phenomena on its processes has yet to be definitively demonstrated. This lack of concrete evidence, paired with the challenge of testing quantum effects in the brain's warm, noisy environment, means that much of the theory surrounding quantum consciousness is still beyond the reach of current science. Yet, this uncertainty should not deter us. Instead, it should encourage us to continue questioning, exploring, and expanding our horizon. In contrast to the rigorous scientific skepticism that often seeks to define boundaries and limit possibilities, the human spirit is inherently curious and open to the unknown. The mystery of quantum consciousness appeals to our innate desire to understand our place in the universe and the nature of our existence. This curiosity pushes us to explore the unknown, to venture beyond the confines of what is immediately observable and predictable, and to imagine new realities that we have yet to encounter. Throughout history, humanity's greatest breakthroughs have often been born from the willingness to embrace uncertainty and to explore the uncharted. Whether in the realms of science, art, or philosophy, our greatest achievements have come from questioning the very nature of reality and seeking answers to questions that seemed, at the time, impossible to resolve. The potential of quantum consciousness lies not just in answering questions, but in transforming the way we see the world. Imagine a future where the mysteries of the mind and the universe are no longer seen as separate domains, but as deeply interconnected aspects of the same reality. A future where human consciousness is not a mere byproduct of neural activity, but a quantum phenomenon that extends beyond the brain, perhaps a universal awareness that taps into the fundamental processes of the universe itself. This vision, speculative, holds infinite potential. It could lead to new ways of understanding the nature of self-awareness, creativity, and reality itself, as well as unlocking new dimensions of human experience. Yet this journey is not without its challenges. The path to understanding quantum consciousness requires not only advancements in quantum physics and neuroscience, but also an openness to new ways of thinking, new ways of being. It demands that we suspend our disbelief and be willing to explore ideas that seem far beyond the conventional. The scientific method, with its emphasis on evidence and falsifiability, must work hand in hand with philosophical inquiry and imaginative thinking. Only through the combination of rigorous scientific exploration and boundless curiosity can we hope to unlock the mysteries of consciousness in the quantum realm. Ultimately, quantum consciousness presents us with an opportunity to embrace the unknown, to confront the limits of human understanding and challenge them, to push beyond the horizon of what is currently possible. The mystery of consciousness, entwined with the mysteries of the quantum world, holds the key to a future where our understanding of both the mind and the universe is expanded in ways that we are only beginning to fathom. As we continue to explore this infinite potential, we may find that the journey itself is as valuable as the answers we seek.